Okay, so we've just outlined that there are two different decisions and conclusions. So the end of a hypothesis test, right? The end to the question about the population ends one of two ways. Either we say we reject the null hypothesis and conclude that we have enough evidence for the alternative, or we fail to reject the null hypothesis and say there's not enough evidence for the alternative. That sounds great, but that leads to four different scenarios. The first two scenarios come from rejecting the null hypothesis. If we reject for the null hypothesis and conclude for the alternative, and it turns out that the alternative is true, then we've made the right decision. But if we reject the null hypothesis, we conclude in favor of the alternative. We say the mean length of a phone call has gone up, but it turns out the null hypothesis is true and the length of a call is really, in reality, the same as it has always been, then we've made the wrong decision, and this is called a type 1 error. A type 1 error is when we reject the null hypothesis, but the reality is that the null hypothesis is true. The second scenario occurs when we do not reject the null hypothesis. If we don't reject the null hypothesis, which means we conclude against the alternative, we say there's not enough evidence for the alternative, if we don't reject the null and the null is true, we've done the right thing. But if if our evidence leads us to not reject the null hypothesis, and therefore we do not conclude for the alternative, we say things like, there's no evidence that the mean length of a phone call has gone up. But the reality is that it has. Well, then we've made an error. And it's called a type 2 error. A type 2 error is when we fail to conclude in favor of our alternative, but we should have, because it's true. We just didn't have the evidence to see that. Here's those two types of error summarized in this table here. The problem is that the reality of whether the null or the alternative is true is not known. The only way to know this, is to have full population data. And we rarely have full population data. That's why we're going off a sample to begin with. So we have to make a decision. But we have to understand that when we make a decision based on a sample, we make our conclusion based on a sample, and usually just a sample, there is always a risk of error. There is always a risk that we got it wrong. And so we want to be able to sort of like, well, how likely are we to have gotten it wrong? So the probability of a type 1 error is denoted by the Greek letter alpha. I draw it like this. It's the Greek letter alpha. And the probability of a type 2 error is denoted by the symbol, this guy right here. This is what mine looks like. That's the Greek letter beta. Our focus is really going to go to the probability of a type 1 error. A type 1 error is when we reject the null hypothesis, we conclude for the alternative, but the null hypothesis is really true. In a court of law, a type 1 error is when we find someone guilty, but they're really innocent. We don't want to do that. We don't want to do a type 2 error either. But in statistics, we start by focusing on a type 1 error and making sure it doesn't happen. So essentially what we do in statistics is we say, okay, there's a maximum, there's a largest value of alpha that I'm willing to accept. There's a largest value of alpha, type 1 error, that I'm willing to accept. And we set that at the start. We set the maximum acceptable level of alpha. And we call that the significance level. Of the test. We call that the significance level of the test. And we only reject the null hypothesis when the probability of a type 1 error is less than that significance level, is less than the maximum value that we're willing to accept. So let's just dig into this a little deeper here. In number 16 that you see on the screen, it says that federal law requires that a jar of peanut butter that is labeled as containing 32 ounces must contain at least 32 ounces. Fair enough. A consumer advocate feels that the certain peanut butter manufacturer is shorting its customers by underfilling its jars. So this lays out a hypothesis testing scenario where mu represents the mean amount of peanut butter in the jars. We have this, it's got to be 32, right? That's what the label says. But we have a consumer advocacy group that believes that it's less than that, right? They're underfilling their jars. They're shorting their customers, right? So there's our competing hypotheses. So the consumer advocate, they go out and they get a sample, right? And then they're eventually going to make a decision. And that decision's either right or wrong. So in number 38, they say refer to that scenario and think about what a type 1 and type 2 error would be, and think about what the consequences of that would be. So a type 1 error occurs when we reject the null hypothesis and conclude for H1. In this scenario, that would mean that we conclude that the manufacturer is underfilling, right? So maybe we file a lawsuit. Maybe we file a lawsuit. Oh my goodness gracious, they're underfilling the jars of peanut butter, right? We're going to file a lawsuit against the company. You're not giving me enough peanut butter, okay? Now, how would that be an error? That would be an error, right? Type 1 error would be if the reality is that the null hypothesis is true, which would mean that the mean amount is really what it should be, 32 ounces. So we file a lawsuit, and it turns out we're wrong. A little egg on the face, right? Like, we're trying to support the customers. We had some evidence that you were underfilling. We're sorry we were wrong, right? Okay, that's the consequence of a type 1 error. What's the consequence of a type 2 error here? A type 2 error is when we fail to reject the null hypothesis, which means that we conclude essentially kind of like against H1. We say that we don't have evidence of underfilling. And so we don't file that lawsuit, right? We don't sue them. We don't file that lawsuit. How is that an error? Well, that's an error if the reality is that H1 is true, right? It's an error if the truth of the matter is that they are, in fact, underfilling. And so that the mean amount of peanut butter is really less than 32. So we didn't sue them, but they're really underfilling. So what's the consequence there? Well, that means that people are getting cheated out of their peanut butter, and we as the consumer advocate group didn't do anything about it. So I don't know about you. The rest of this is an opinion, right? Like, which one is more serious? That's for you to decide. But I know for sure that I really don't want to file a lawsuit and be wrong. I mean, if it happens, I don't know how to pay for lawyers, right? So I'm thinking about a type 1 error scenario. I don't really want that to happen. It's going to cost me a lot of money to file a lawsuit only to be wrong. So what's the maximum likelihood of that? I don't want to make an error more than 5% of the time, 10% of the time, 1% of the time. I want my error to be unlikely. So maybe I'll set this sort of like maximum likelihood of a type 1 error. Maybe I set that at 5%, right? Maybe I set this maximum acceptable likelihood of a type 1 error at 5%. Maybe, I don't know, maybe I set it at 1%. I really don't want to spend money on lawyers only to be wrong. This is the decision that has to be made before you start your test, right? Before you actually start digging into your sample evidence. How likely is it that I'm going to be wrong? I don't want to be wrong and make a mistake and spend a lot of money only to find out that I'm wrong more than 1% of the time, 5%, 10%. Those are the most common levels of significance. And so in summary here, this is in general how we'll eventually get to how we make our decision to reject or not reject. We will reject our null hypothesis only if the observed sample is very unlikely to have occurred when the null hypothesis is true. What defines very unlikely? In the past, we've used 5%. Moving forward, we're going to use anything less than alpha, anything less than the maximum acceptable likelihood of a type 1 error. So what are we going to do? We're going to set up our hypotheses about the mean or the proportion. We're going to consider the sampling distribution. Remember, there are conditions on whether that's normal or not. We're going to look at the observed value of our statistics, and we're going to ask how well does it fit into that distribution. Remember, we assume the null hypothesis is true. And we say, okay, how well does our sample statistic fit in there? That's called that measurement's called a test statistic. That's going to be a Z or a T score. Then we're going to measure the likelihood of something like that. We're going to measure the probability of a statistic like that. That's called the p-value of the test. And if that p-value is small, in fact, smaller than alpha, then we will reject the null hypothesis, and only then will we reject the null hypothesis. Here's what it looks like in practice. In 2019, 59% of Americans said they did not trust the media when it comes to reporting the news fully, accurately, and fairly. In a 2021 poll of 1,310 adults nationwide, 811 stated they did not trust the media. At the alpha equals 0.5 level of significance, so in other words, they're saying they're not willing to take more than a 5% risk of getting this wrong. They're asking, is there evidence to support the claim that the percentage of Americans who do not trust the media to report accurately and fairly has increased? So our hypotheses involve that 59%. Our null hypothesis is that it's 59%. It's what it used to be. The null hypothesis is that it's increased, right? This would be important to know. Have people lost trust in the media from 2019 to 2021? So we look at our sample proportion. It was 811 out of 1,310, which is about 62%. So p-hat is about 0.62. And then we look at that in terms of the sampling distribution. So over here we have the sampling distribution of p-hat. Now it's been standardized so that assumed value of 0.59 would have a z-score of 0. And then our sample statistic, that p-hat of 0.62, would have a z-score of 2.14. 2.14. So that test statistic means that if the null hypothesis were true, getting a p-hat of 0.619, right? That's more than 2 standard deviations above the hypothesized value of 59%. So we measure how likely that is by looking at this area under the curve here. What's the probability of getting a p-hat at 62% or higher? Probability of a p-hat at greater than or equal to 0.62. What's the likelihood of getting that? And it turns out that that area, that p-value, is 0.0162. It only happens 1.62%, or approximately, or less than 2% of the time, right? So in a sample, if we took 100 samples, we would only see a p-hat that high about twice, less than twice, maybe once, 1 or 2 times. That's unlikely, right? That's unlikely. That's unusual. We got an unlikely result. The p-value of 0.0162 is less than the significance level of 0.05. It occurs less than 5% of the time. That's unlikely enough to reject the null hypothesis and conclude that there is evidence that the percentage has increased. That's what a hypothesis test is going to feel like. We'll dig more into it next week.